This lecture is specific to Conceptual Physics AB. In this lecture, we cover what is called the simple pendulum. Let me go ahead and set a pendulum into oscillation like so. And the pendulum is oscillating about its equilibrium position, which is at the bottom of the swing. Now, we've already described pendulums prior to our unit here on oscillations, and we did so in the context of energy transfer. So, for example, gravitational potential energy is transforming back and forth into kinetic energy as the oscillation occurs. What we're interested in describing, however, in this lecture are some of the parameters associated with the oscillation of a simple pendulum. Okay, let me go ahead and re-tilt the phone back towards the board. Let me tilt it up as well. Okay, so now we take a look at some of the details here associated with the simple pendulum. The simple pendulum is another example of a simple harmonic oscillator. It's oscillating about its equilibrium position, which is at the bottom of the swing. Once again, we've talked about this already in the context of energy transfer. Here we discuss the parameters of the oscillation itself. So let me go ahead and draw out the pendulum in profile like so. We have a mass M and the pendulum has a length L associated with it. Right here is the vertical direction. The bottom of the swing is considered to be the equilibrium position, and then the oscillation occurs like so along a circular arc. The most important parameter that describes the period of the oscillation is the length of the pendulum. The period of the motion is described by the following expression, where L is the length of the pendulum. Notice that this expression looks pretty similar to the period equation associated with a mass attached to a spring. And then like that equation, deriving this expression here for the period of a pendulum is beyond the scope of this class when we apply F equals ma to the situation. However, let's just examine the basics here of the expression itself. The frequency, once again, by the way, is equal to the reciprocal of the period. Okay, when it comes to the period, however, it's the length of the string that's the most important parameter. So let me go ahead and demonstrate this to you in the following way. I'm going to tilt the phone once again. So bear with me here as I do. Like so. Okay, and now it's the length of string L here that's the most important parameter when describing the period of the oscillation. The longer the length of the pendulum, the greater the period. The larger the period, the smaller the frequency. So for example, compare the period of the pendulum here with a relatively long length L to say the period of the pendulum's oscillation like so when the length L is smaller. When the length L is smaller, the period is smaller, and then therefore the frequency is higher. Like for a mass attached to a spring, notice that the equation that describes the period does not depend upon the amplitude of the motion. Once again, the amplitude is the maximum displacement from the equilibrium position. So let me set this into a small amplitude oscillation like so. The amount of energy that's present here is small. But let's say that, for example, with a stopwatch, I measure the period, I measure the time necessary for one oscillation. That would be exactly the same as the case where I give, for example, the pendulum a greater amplitude. The time necessary for one oscillation here is exactly the same as it was a moment ago with the smaller amplitude. In this particular case, the amount of energy that's present is greater than it is with a smaller amplitude oscillation, but the time necessary for one oscillation here is exactly the same as the time necessary for one oscillation here. Therefore, we could use a pendulum, for example, as a timing element in order to keep track of time. And in fact, the very first accurate mechanical clocks that were built at the end of the 17th century were all pendulum clocks. Okay, let's go ahead and take a look at a couple of basic examples associated with the equation for period. And I'm going to remove the phone once again. Like so. Let me tilt it up a little bit as well. Okay. Okay, and now we have two basic examples for us to look at here with respect to the simple pendulum. Go ahead and copy the first of those examples into your notes. So a simple pendulum has a length of 80 centimeters. That's, by the way, the length of the pendulum that I'm using to demonstrate. So we're given that L in the example is 0.8 meters, that's 80 centimeters, and the pendulum oscillates in simple harmonic motion. Part A, what is the period of oscillation? And then part B, what is the frequency? So in part A of the example, all that we're going to do is plug into the expression here, where of course G, acceleration due to gravity, is 9.8 meters per second squared. So let's now go ahead and calculate the period by using a calculator. Let's see, where is my calculator? Hang on one moment while I locate my calculator. Okay, so let's just go ahead and plug in. So 2 times pi and then multiply by the square root of L over G. So 0.8 meters divided by 9.8 meters per second squared. And this then gives me a period of about 1.8 seconds. So that's the period of the pendulum that I was using to demonstrate a few moments ago. Okay, then in part B, let's just go ahead and calculate the frequency. This is the number of oscillations made per second. So we just take the reciprocal or the inverse of 1.8 seconds. And this comes out to be about 0.56 or so hertz. So about half an oscillation is made per second with respect to my pendulum demonstration. Okay, then there's going to be a second problem. We'll take a look at that second problem in the next video.